everyone. Today I'm excited to introduce you to the fascinating world of thermodynamics in renewable energy technologies. Our group consists of 4 members, include me as Nurna Suha binti Muhammad Razilam, Anissa Sofia binti Naim Shauki, Ayu Najiha binti A. Rashid, and Shamimi Amani binti Syari. The content of this topic include introduction, thermodynamic principle, application on renewable energy, challenges and innovation, and the last one is conclusion. So, what exactly is thermodynamics? In simple terms, it's the study of heat, energy, and work. Understanding thermodynamics is crucial because it governs how energy is transferred and utilized in various systems. So, why should we care about thermodynamics? Well, it's crucial for understanding how we can make our energy system more efficient. We can design systems that use energy more effectively, cutting down on waste and costs. This is especially important in our fight against climate change. Efficient energy systems help lower greenhouse gas emissions, making them vital for a healthier planet. Now that we have a basic understanding of thermodynamics, so let's explore its key principle. The first law of thermodynamics states that energy cannot be created or destroyed. It can only change forms. This means that when we harness renewable energy, we are simply converting one type of energy into another. Next, we have the second law of thermodynamics. This one is particularly interesting because it reveals that energy transformations are not perfect. There's always some loss, usually in the form of heat. This is why understanding this law is vital for improving our renewable energy technologies.
Now, let's talk about the application of renewable energy. Solar thermal energy systems are one of the most significant applications of thermodynamics in renewable energy. These systems use sunlight to generate heat, which can then be converted into electricity or used for direct heating. The most common types are concentrated solar power CSP systems, such as parabolic trough and solar power towers. In CSP systems, sunlight is concentrated by mirrors onto a receiver, where it hits a fluid like water or molten salt. This heated fluid is used to produce steam, which drives a turbine to generate electricity. The thermodynamics of these systems are governed by the Carnot cycle, which defines the maximum theoretical efficiency based on the temperature difference between the heat source, sunlight, and the heat sink ambient environment. The greater the difference between the heat source and the heat sink, the higher the potential efficiency. However, the efficiency is still limited by practical factors like heat losses and the inherent limitation of the Carnot cycle. Thermodynamic optimization in solar thermal technologies focus on improving heat collection, reducing losses, and maximizing the temperature gradient for higher efficiency. Wind energy is another prominent renewable technology driven by thermodynamics. Wind turbines convert the kinetic energy of the wind into mechanical energy, which is then used to generate electricity. The efficiency of this process is governed by Biggs law, which states that no turbine can capture more than 59.3% of the wind's energy. This is because as wind passes through the turbine blades, it slows down, and if it slows down too much, the turbine will lose efficiency. The efficiency of wind turbines depends on factors such as wind speed, air density, and blade design. Optimizing these parameters is crucial to capture as much energy as possible. Thermodynamics models are used to optimize turbine placement, blade design, and operation to improve overall performance, ensuring maximum power generation in varying wind conditions.
Next, we move to closed cycle or TEC. Or TEC is a technology for generating renewable energy that uses the temperature differential between the deep cold and relatively warmer surface waters of the ocean to generate baseload electricity. A TEC is a heat engine system with a heat source and a heat sink. The warm water passes through a heat exchanger, which is in contact with a closed loop of working fluid. The warm water evaporates the working fluid into a vapor which expands and drives a turbine. The turbine connected to a generator, which is the source of the mechanical energy. The generator converts the mechanical energy into the electrical energy. After the vaporized working fluid passes through the turbine and generator, it enters another heat exchanger, which is in contact with the cold water. The vaporized working fluid is condensed back into liquid, which is then pumped back into the evaporator to complete the cycle. Both cooled warm water and the warm cold water are discharged into the ocean after they have passed through the heat exchangers. The last application is geothermal power plants. Geothermal power plants draw fluids from underground reservoirs to the surface to produce heated materials. There are three main types of geothermal power plant technologies, which dry system, flash system, and binary cycle. However, we'll just focus on flash system plants, which is the common type of geothermal power plant in operation today. Fluids at temperature greater than 182 degrees Celsius pumped from the deep underground travel under high pressures to a low pressure tank at the Earth's surface. The change in pressure causes some of the fluid to rapidly transform or flashed into vapor. The vapor then drives a turbine, which drives a generator. If any liquid remains in the low pressure tank, it can be flashed again in a second tank to extract even more energy.
Now, let's go to the challenge and innovations of thermodynamics in renewable energy technologies. One of the most significant challenges in renewable energy technologies lies in the inherent limitation imposed by thermodynamics. For example, the second law of thermodynamics dictates that no heat engine can achieve 100% efficiency, meaning energy losses are inevitable. In solar thermal system, this inefficiency is amplified by heat dissipations and conversion losses, which prevent them from reaching their full potential. Similarly, the intermittent nature of renewable sources like solar and wind creates variability in energy input, making it difficult for thermodynamic system to maintain consistent performance. Geothermal energy, on the other hand, often produces a low-grade heat, which is challenging to convert efficiently into usable electricity. Furthermore, the material used in this system face significant thermal stress due to extreme temperature and frequent cycling, leading to wear and tear, reduced reliability, and higher maintenance costs. Together, these factors create complex hurdles that hinder the optimizations of renewable energy systems. Remarkable innovations are paving the way for more efficient and reliable renewable energy technologies. For instance, advanced thermodynamic cycles like the supercritical CO2 cycle operate at a higher efficiencies and with a lower environmental impact compared to traditional Rankine cycles. Thermal energy storage is another area of innovation, with phase-change material and molten salt enabling the efficient storage and retrieval of heat for use during non-peak hours. At the material level, new high-performance material, including ceramics and nanomaterials, are being developed to withstand extreme conditions, improving durability and thermal efficiency.
In conclusion, thermodynamics is fundamental to the development of optimization of renewable energy systems. Its principles help us understand energy transformation, enabling the design of more efficient technologies like solar thermal systems, wind turbines, and ocean thermal energy conversion systems. While these systems face challenges such as inefficiencies, intermodalities, and material limitations, advancement in thermodynamic cycles, energy storage, and high-performance materials are driving significant improvement. With continued innovation, renewable energy has the potential to meet global energy demands and sustainably, paving the way for a cleaner and more resilient future.